Hello, this is a follow-up to making a connection between the transformations of parent graphs of, in this case, a circle and a parabola. We graphically figured out how to figure out where they intersect. Now let's talk about how to do it algebraically. So in this case, there are more than one way to do this, but either you can think about using the methods of equal values method, substitution, or elimination. Those are our algebraic ways of, finding points of intersection. But it really depends on the structure of your equations. So looking at these two equations here, you might think, well, I could use equal values method, but this top equation is not solved for y, so that doesn't really make sense. Because I would have to solve for y, and that would take a lot more work. So what is another option? Another option would be to do substitution. So looking in one of these equations, is there anything I can easily substitute? And you can see it in two different ways. Number one, I see an x squared here and I see an x squared here. So I could, solve the second equation for x squared and then substitute in y plus 4 for that. And so that's like one option. Or the other option is to substitute in, again, for this, I can isolate this x squared and then substitute in the 25, again, minus the y minus 1 quantity squared here. So it doesn't really matter. Part of it is like, let's just try it. So I'm just going to label this like EQ number 1, and I'm going to label the other equation EQ number 2. And so then I can refer to each equation. So I'm going to first try to, I'm just going to rearrange. I'm going to rearrange EQ number 2. And if I do that by solving for the x squared, I would get y plus 4 equals x squared. And then I could substitute into equation number 1. So take a moment, maybe pause the video and try to do this yourself. If I am looking in equation number 1, I again see that I've got x squared and I've got an x squared up here. So I'm going to go ahead and substitute in the y plus 4 for that whole entire x squared. And then we've got plus the y minus 1 quantity squared equals 25. Now you can see I have one equation with one unknown, and I can actually solve this. And at first I'm going to be solving, in this case, for y. So as a reminder, you need to expand the y minus 1 squared. So what does that really mean? If you need to create a quick little area model to actually multiply this out so you don't forget about that middle term there. Or you could use distributive process, but if I create a rectangular area model, that's y squared minus y, and then positive 1. These two right here are like terms, so those combine to negative 2y. So let's simplify what I've got left. Y plus 4 plus, inside the rectangle was the y squared minus 2y plus 1 equals 25. I need to collect some like terms here and here. And again, the constants can be also combined together here, and I'm going to bring the 25 to the other side. So I've got a y squared, and then the y and the negative 2y make a negative y. And on this side, I've got 4 plus 1, which is 5. And when I subtract 25, from both sides, it would actually end up with a negative 20 over here. And the reason why I kept every term on one side of the equation was I recognized I had that quadratic term there. And that quadratic term really dictates the fact that I am going to need to factor this to solve it. So I'm going to use a diamond and figure out what multiplies to negative 20, y squared, and also adds to negative 1. And so in this case, 4 and 5. If one of them is negative, and since they need to combine to a negative 1, it's the negative 5 and a positive 4 that would add to a negative 1 but multiply to a negative 20. And so again, since the a value here is 1, it just becomes the y plus 4 times the y minus 5 equals 0. And now again, you use zero product property to figure out when is y plus 4 equal to 0, or the other one, when is y minus 5 equal to 0. And solving each one of these, it's when y equals negative 4 or y equals positive 5. That, however, is just the y value. Points of intersection are coordinates. So you got to go back and figure out what the corresponding x value is. So we need to find the x value. that corresponds to each one of those particular y values. So I've got like an equation that's already solved for x, this one right here, x squared equals y plus 4. So let's go ahead and do that. We've got x squared equals, well, the y, negative 4, right, plus 4. So that means x squared equals 0. So that's x equals 0 because there's no plus or minus 0. So therefore, one of the points of intersection occurs when the x value is 0, 0, and the y value is negative 4. So notice my graph, I graphically figured out that point of intersection. But I also have other points of intersection because I need to also figure out the x values that correspond to that y value. So again, if we have x squared equals, and again, I'm using this equation here, already isolated for x, and now we have 5 plus 4, and 5 plus 4 is 9. So we got x squared equals 9. Now, if there's an unknown value that equals a positive 9, there are two values that make this true. Either x equals 3 or negative 3. So there are two x values here. So therefore, either x equals 3, 5, or x equals negative 3, 5. I hope this helps with supporting you to figure out this extension to our lesson today.